Okay, well, in this video, I wanted to make a brief introduction into what is a PID controller. Okay, so in the previous, in a previous class, okay, what I did was to show you how you can generate a mathematical model of a system, no? In particular, we analyze mechanical systems. And also I made the analysis of a electrical system, no? In particular, an RC circuit. But I want to retake the analysis of this spring mass damper system, in which we say that we are applying a force to the mass, and we want to generate a model, okay, that relates the force that I am applying to the mass with the position of the mass, okay? In this case, X is the position of the mass. And I show you that you can generate what we call a transfer, okay, a transfer function, okay, of the system. And the transfer function basically relates in the S domain the relationship between the output of the system, that is the position, with the input of the system, that is the force. But we are generating this mathematical model in the S domain, and we show that the transfer function of this spring mass damper system is given by m times s squared plus b times s plus k. Okay. Also, we discussed that, well, you can't compute the important dynamics of the system if you compute the roots of the polynomial in the denominator. That is, we solve the following equation for S. Okay. So if I compute the roots of this polynomial using the quadratic formula, that is equal to minus b divided by 2a plus and minus the square root of b squared minus 4 times a times c. This is the quadratic formula. I can use this quadratic formula to compute the roots of this polynomial. So I can say that m is equal to a, b is equal to b, and k is equal to c. Okay? So this is equal to s is equal to minus b plus and minus the square root of b squared minus 4 times a, that is the mass, times c, that is k in this case. And this is divided by 2 uh, times m, no? And this is the roots of the polynomial, okay? Then here I am using an algebraic expression for the roots because I don't know the value of the coefficients, where I can use values for m, for b, and k for this polynomial, and use the values of m, b, and k in order to, well, solve this algebraic expression, no? But the important part is that also I told you that, well, if based on the values or the sign of the terms inside this root, okay, I can get imaginary roots or not. For example, if the value inside this root is lower than 0, okay, that means that I can generate complex roots, and that is associated with an oscillatory behavior, okay? But if I get uh, the value inside this root, okay, is greater than 0, that means that I will not get an oscillatory behavior, and I will get only a damping behavior, okay, for the system. And this depends mainly on the values of the damping coefficient and the constant of the spring, okay? And in this case, if I use a very big damping coefficient, well, I will get a positive root, okay? But in case I am using a very small damping coefficient, I will get the value inside this root will be lower than 0, and I will get oscillations in the response of my system. Okay, so that is why we are interested in computing the roots of the denominator of this polynomial, because using these roots we can compute the poles of the system, no? The value of these roots are also the poles. Okay, these are the poles of the system, and also we call them eigenvalues, okay? That basically the eigenvalues of a dynamical system are the most important dynamics. And well, we use MATLAB to compute the response of the system. Basically, in general terms, we have here the transfer function, and we input a value for force. And based on this input force, we want to measure the position of the system. Okay? And we call this, or we can name this type of analysis, the open loop response. Okay? And well, also I told you that you can change the dynamics of the system, or you can control in a way the dynamics of this system, no, this transfer function, if we set the values of n, b, and k. In particular, if I choose a very big damping coefficient, I can reduce the oscillation of the system. But if I use a very big constant of the spring, I will have a greater oscillations compared to the damping. Okay. So you need to be very careful into how you are setting these coefficients. Okay. But sometimes, or the real challenge is that in a for a real world application, we cannot change the value of these coefficients, no? We cannot change the mass of the system. We cannot change the constant of the spring or the damping coefficient, no? Maybe the system behaves in that way, no? But still we want to control those dynamics. We want to change the dynamics of the system. Okay, so since we want to change the dynamics of the system, well, we cannot change the system itself. We need to find a way to change virtually, no? I will put it in that way, to change virtually the dynamics of the system without altering the actual system, no, the actual physical system. So the idea is that we have again the system, no, that we want to control, and I can use a controller, no? I can use a controller in which that is basically an algorithm that will tell me what is the necessary force that I need to apply to my system in order to move it into the position that I want. Okay? So the controller is basically an algorithm. In fact, I can program this algorithm in a computer like a microcontroller or a PLC, and I can embed this controller into those computers, and the controller will tell me what is the force that I need to apply to my system by considering this transfer function in order to move the system into the position that I want. Okay? But the controller requires a very particular time of input. Okay? So the input of this controller is set as follows. Imagine that you have a desired position. No? We have a desired position, and we want to use this desired position as a reference, no? No, this is the position that I want. And I will compare this desired position, okay, with the actual position of the system. So basically, I am using this cable as a sensor, no, to simulate the presence of a sensor that I am placing in this system in order to measure the position, okay? So I can measure the position of my spring mass damper system, and I can compare the actual position that I am measuring with the desired position that I want. And the difference between the desired position that I want for my system and the actual position that I am measuring from the system produces an error, okay? And the error is basically the difference between the desired position, no? I will put it like in this way, the desired X minus the measure X, okay? So this is the value of the error. And I will use this error as an input into my controller, okay? And the controller will take these values of the error in order to set the adequate force that you need in order to place the mass into the position that you want, okay? But the important factor here is that we adding this controller, no, that will help us to set the adequate force that we need to apply to the system based on the error that we are computing, based on the difference between the position that I want and the position that I am measuring, okay? So I can use this error into my controller, and the controller will generate automatically the force that we need to apply to my system in order to move it in the way that I want. And by using this type of architecture, I can change the dynamics of the system. Okay, no, I can see how I can control automatically the dynamics of the system without altering the actual system. I am not changing the transfer function that I used previously. No, this is not change. No, this is invariant. No, we can say that is invariant. The coefficients of this system are not changing, but what it is changing is the force that I am applying to the system based on the error, okay, that I am computing. And this is called the closed loop response of the system, okay? Now, the question is, well, how can we know what is the controller that I can use? And there are many types of controllers, no? You can have, I will name some of them like the linear, quadratic regulator. Also, we have the, what other one? We have the sliding, okay, sliding mode control, no? Also, we can use artificial intelligence. For example, I can use an artificial um, neural network, okay, to determine the optimal controller. And I can also use, for example, reinforcement learning. Okay, I can use reinforcement learning. Okay, that is one of the branches of artificial intelligence. Okay, so there are different strategies. In fact, one of the most popular ones to control autonomous vehicles is reinforcement learning. Okay, and in the jargon of reinforcement learning, the controller is called, no, the controller is basically called the agent. Okay, and the system, no, is referred as the environment. Okay. And this is like making like an analogous comparison with the jargon of reinforcement learning, because reinforcement learning has well, other applications, no? You can apply reinforcement learning, for example, to train a large language model. You can use reinforcement learning to tell a machine how to learn a video game, for example, no? But basically, this is like the analogous comparison with the theory of control engineering. And the main difference from my point of view is that in reinforcement learning, we are considering that there is some undeterministic behavior, no, in the environment and also in the controller, okay? In fact, the agent can be a neural network, no, that we are feeding in order to interact correctly with the environment, or in this case, with the system. But regardless of all these types of controllers that exist in the literature, the most popular one and also the most effective one is the PID controller, okay? And the PID controller stands for the proportional, okay, integral, and derivative controller, okay? So the PID controller stands for proportional, integral, and derivative controller. And this is one of the most popular controllers and also is widely used in industry, okay? And the reason for that is that it's very simple to use. And also the operations that you need to use to define the adequate force that you need to apply to your systems is there. Well, the equations or the mechanisms is relatively simple. And also we can find like a physical interpretation of what is doing this PID controller. Okay. So basically, this PID controller is performing the following. Remember that here we are considering that the error is the input into the controller. So the PID controller is basically doing the following. In fact, the force that is output by the controller can be defined as follows. The force is equal to the error multiplied by a constant, okay, that I label Kp, and this Kp stands for the proportional control action, okay? The meaning of proportional is that basically we are multiplying the error by a gain value, okay? Plus the integral action. And the integral action basically means that we are computing the integral of the error across time. But we are multiplying the integral of this error by a constant that I will label chi sub I, okay? This is the integral gain, okay? Plus the derivative of the error with respect to time. This is the derivative action. And we can multiply this derivative by a gain labeled as k sub d, okay? So we can say that this controller is basically computing the following operations on the error, okay? And based on these operations, we can define the adequate force that we need to apply to our system in order to control the trajectory, or in this case, the output of the system very effectively, okay? So this is the idea. Now we have the following structure for the PID controller. And, and, mm, mm, and well, what else? Well, with this information, we can compute the force, no, that we need to apply to the system. Okay, so, well, in a following video, I will explain how we can use Simulink in order to first program this controller by considering the dynamics of the system. In particular, I will be analyzing this spring mass damper system that we analyzed in the previous video or in the previous class. And based on this, you can see that it is very easily to define this controller or to program this controller. The important factor here is that, or the challenge, no, if we can put it in a way, is to define the adequate values of these gains. Okay, so there are like many procedures in which we can define the value of the proportional, the integral, and the derivative gains. But I will show you like an empirical and also steps that you can follow to always define correctly, or to the best you can, the value of these gains. Okay, I think that that is the better approach, because we can see by using a simulation and also empirically what is the effect of these actions into the dynamics of the system. Okay, but you will notice that by applying these three control actions, we can control as we want the dynamic response of at least this type of systems. Okay, so that's all for this video, and see you later. ¿Qué haces aquí, Julia? Escuchándote, ¿por qué me va a